Okay. So, let us start that last class we have said that if the real spectrum is Cn, then it is nothing but a complex spectrum is Xn plus complex spectrum of minus n, then divided by 2. This we said. If the Xn is the complex spectrum and Cn is the real spectrum. Now, we will go for the proof of it. Can we prove it? Yes, we can prove it. So, now I want to prove it. So, what we will do? First think about the real spectrum. What is Cn? Real spectrum means inverse Fourier 2 pi minus pi to pi. What is that? Inverse Fourier of log magnitude, log of x, I can say e to the power j omega mod of that log, okay, e to the power j omega m d omega or n, sorry, e to the power j omega n d omega. This is the real spectrum. Okay. If it is real spectrum, then if I compute this one, what is e to the power j omega n? E to the power j omega n can be replaced by 2 pi minus pi to pi log of mod x e to the power j omega n into the j omega cos omega n plus j sin omega n e to the power j theta cos theta plus j sin theta into d omega. Now, if you see that Xn is real, if the input signal is real, then we said the real spectrum Cn is nothing but the even function, So, if it is even function, then I can say that if this only exists cos term, sin term cannot be exist. That means 1 by 2 pi minus pi to pi log of x e to the power j omega into cos omega n d omega, because log of minus pi to pi log of x e to the power j omega mod into j sin omega n d omega is equal to 0, because this is the even part. So, even part is 0. So, only the odd part is exist. Okay. So, Cn is equal to 1 by 2 pi minus pi to pi log of e to the power j omega cos omega n d omega. This is proof. Now, find out the, so this Cn I can write down Cn in here in one corner. So, later on we can use that. So, in one corner I write down Cn is equal to minus pi to pi log of x of e to the power j omega then mod cos omega n d omega is the Cn. Now, what is complex spectrum? Now, complex spectrum, if I say this is x cap n is my complex spectrum, it is nothing but a 1 by 2 pi minus pi to pi x of log. So, there are two parts, one is you can say log x e to the power j omega d omega or not, e to the power j omega n d omega. Okay. Now, what is this? This is a complex function. So, I can say log of x e to the power j omega is nothing but a log of mod of x e to the power j omega plus, so if I take the log of theta component, so a plus jb can be expressed as root over of a square plus b square, which is nothing, suppose this is x. So, it is nothing but a mod of x into e to the power j theta. So, if it is e to the power j theta, then if I take the log, so it is nothing but a plus j arg j arg x of e to the power j omega So, I can replace this x e to the power j omega by 1 by 2 pi minus pi to pi log of x e to the power j omega mod plus j arg x of e to the power j omega, okay, x arg e to the power j omega into e to the power j omega n. So, e to the power j omega n, again we can write cos of omega n plus j sin of omega n d omega. Now, there is a two term, a plus b, let us c plus d. So, fourth term will be there. If I multiply, there will be a fourth term. Again I can say the if for xn is real, if xn is real, then odd component minus pi to pi. So, I can say that arg e to the power j omega e omega, only the odd component exists, only the odd function exists. So, this multiply with cos omega n will be 0. Similarly, if this multiply with sin omega n will be 0. So, then what we get, instead of fourth term, two term will be 0. If two term 0, then this will be 1 by 2 pi minus pi to pi log of x e to the power j omega mod cos omega n will only exist d omega plus 1 by 2 pi minus pi to pi j. So, j and j multiply will give me minus 1. So, minus I can say arg of x e to caps x e to the power j omega sin omega n d omega. Okay. So, this is x n. Now, what is my x of minus n? This will be only plus. So, it is nothing but a 1 by 2 pi minus pi to pi log of x of e to the power j omega. So, this is capital X mod plus 1 by 2 pi minus pi to pi arg x of e to the power j omega sin omega n d omega. So, if I add this x of k and x plus n, so if I add these two terms, what will I get? So, if I add this term will be cancelled, only these two term will be there. So, I can say it is nothing but 2 into 1 by 2 pi minus pi to pi. So, I can say x cap n plus x cap minus n is nothing but a 2 into this pi to pi log of x of e to the power j omega mod cos omega n d omega. So, if I make this by 2 is equal to this. So, if it is this, then I can say this is equal to this. So, I can say x cap n plus x cap of minus n divided by 2 is equal to C n. So, I can say the real spectra, the real spectrum is nothing but a sum of complex spectrum x of n and x of minus n divided by 2 is proved. So, proof is there in the slide also, you can refer to the slide also. Okay. Now, come to the another one which is called LPC spectrum, which is called LPC spectrum. So, what is LPC spectrum? So, what we said that if I have a x signal and if A1, A2 dot dot AP are my LPC coefficient, those are the LPC coefficient of pth order, then if I take the frequency transform of this, if I take the DFT of this, what I will get? I get LPC spectrum, I get LPC spectrum which is nothing but I can get easily LPC spectrum. If I instead of instead of signal, if I use signal xn and take the DFT, I will get xk, which is called real spectrum, signal spectrum, and this is give me the LPC spectrum. I can use this LPC spectrum to compute the Cepstral coefficient C1, C2, C0, C1, C2, Cn minus 1. If I use the signal spectrum, then I get the Cepstral coefficient Cn. If it is real log magnitude, then it is real. So, real spectrum Cn. Now, if instead of signal spectrum, if I use LPC spectrum, then it is also possible to find out the Cepstral coefficient from the LPC spectrum. So, the parameter name is called LPCC, LPC del Cepstral coefficient, LPC Cepstral coefficient. Okay. So, if it is LPC Cepstral coefficient, how do we calculate it? It is said using this three equation which is given in the slides, and I am writing. So, if A1 and AP are the LPC coefficient and I want to find out the value of C0 to Cn minus 1 are the Cepstral coefficient, real Cepstral coefficient. So, how do I do that? We said that C0 is nothing but a log of G square. What is G? G is called gain, model gain, LPC gain. During the LPC analysis, I have already discussed how to calculate the G for a given signal. So, if I know the G, C0 is nothing but a log of G square, then I can say Cm is equal to Am plus k equal to 1 to m minus 1 k by m into Ck A m minus 1, where 1 is equal to m p. So, if varies from m varies from 1 to p, then I can get C1, C2 dot 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 Cp using this equation. Then it is said Cm is equal to k equal to 1 to m minus 1 k by m into Ck A m minus 1 is if m is greater than equal to p. If m is greater than equal to p, then I get C p plus 1, C p plus 2 dot 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 C n minus 1 using this formula. Okay. So, I get C0, C1, C2, C3 up to Cn minus 1 using this. Similarly, reverse also possible, that if I know the Cepstral coefficient C1, C0, C1, C2, C3 dot 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 Cn minus 1, then I can calculate the p order LPC coefficient. So, A0, A1 dot dot AP. How do I do that? In that case, gain is nothing but a e to the power C0 by 2. This is inverse. C0 is equal to log G square. So, C0 is equal to e to the power C0 by 2. Then I can say Am is equal to Cm minus m equal to k to m minus 1 k by m Ck A m minus k for 1 is equal to m p. So, I can get A1, A2, A3, A4 dot 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 AP. Okay. So, if I calculate the Cepstral coefficient from LPC spectrum using these three formula, I get the Cepstral coefficient from LPC spectrum. So, LPC Cepstral coefficient. If I know the Cepstral coefficient, I can calculate the LPC coefficient using this formula. So, all are the speech parameter. The Cepstral is a speech parameter, LPC coefficient is a speech parameter, and LPC to Cepstral, Cepstral to LPC conversion is possible. Okay. Now, we go for the next topic, which is called MFCC parameter, male frequency Cepstral coefficient. So, there is a many information in the slide. I am not going details of the slides. I just give you the gist. Male frequency Cepstral coefficient and MFCC, this is popularly known as MFCC, which is the most used parameter in speech application. MFCC are used in most of the cases. Most of the cases MFCC is used. Okay. So, compute. So, you can say that there is three simple steps in MFCC compute. Compute FFT power spectrum of the speech signal, apply male filter bank, and then compute DCT. Why? I will come why these steps is required. So, what we said that if I take the spectrum or if I take the spectrum of a speech signal. So, how do you draw the spectrum of a speech signal? You know, if xn is my time domain signal, if I apply DFT, I will get xk. I am not explaining the framing and windowing. So, that also included the speech processing, framing and windowing. Instead of taking the whole signal at a time, I have a whole signal, I cut the signal, I pre-emphasize the whole signal, then cut the signal in a frame, in a window, then shifted the window by a frame. So, framing, windowing, all things I have done, and after that if I take the DFT, I will get xk. Now, if I calculate mod of xk and if I plot with the frequency, then I get spectrum of signal xn. What is that? So, what is spectrum? So, this axis is the k axis, discrete frequency k, and this axis the amplitude of the amplitude mod of xk. So, this is mod of xk axis. So, k equal to 0 I get here. So, I get this kind of speech spectrum, not that smooth, I am drawing it smooth. If you draw it real, then if you see, you get this kind of speech spectrum. I have already explained in last class also. So, if you see, if I take a signal, this is my signal, then if I select this portion, if I analyze it, then if I can, this is the spectrum. So, spectrogram plot of spectrum of the signal, selected signal. So, this axis is the frequency axis, this axis is the amplitude axis of the mod of xk. So, instead of discrete frequency, I can write f also. What are the relations? F is equal to 2 pi by n into k. 2 pi by n is the resolution, where n is the length of the DFT which I have taken. Okay. Now, what is my interest? If I want to extract the speech signal, speech parameter, I interest to find out this resonant frequency. My interest in find out this resonant frequency, and those resonance frequency actually define the speech event which is produced by the vocal tract. So, if I want to find out those resonant frequency, what I can do, let us instead of taking the whole spectrum, I can take a filter kind, design some filter kind of things. So, this is not perfectly done. So, I can just shifted this one in here. So, I can design some filter, let us triangular filter with 50% overlap, let us 50% overlap. So, this kind of filter I can design. Let us uniform bandwidth filter I can design. If I design that, then I am assuming that if this is the peak of my envelope, then power of this, average power of this filter will be very high. So, actually I am try to capturing the formant frequency using spacing some filter along the spectrum. Okay. So, that can be possible. So, suppose I have a, so what is the baseband, if the sampling frequency is Fs, how much n I should take? I should take up to n by 2, because it is symmetry, DFT is a symmetry. So, I can say if it is a Fs, then maximum baseband frequency is Fs by 2. So, if I have a DFT length is n, then I can take up to n by 2, k equal to n by 2 is sufficient for designing the filter. Okay. So, suppose I have a 8 kilohertz, Fs is equal to 8 kilohertz, then I know that maximum speech frequency is 4 kilohertz. So, suppose I take 100 hertz filter, let us linear, all filter are 100 hertz bandwidth. Okay. All filter are 100 hertz bandwidth. So, if it is not overlap, how many filter is required? 4 kilo divided by 100. So, 40 filter is required. Now, if it is 50% overlap, then I can easily find out how many filter is required. Okay. So, how many filter is required I can easily find out. So, now once I know that is how many filter is required, then I can say okay, let us instead of all k design this filter. So, divide, let us 40 filter, let us I have said if it is 50% overlap, how many will be there? 50% overlap means instead of shifting 100 hertz, I am shifting 50 hertz. Okay. So, I can say 80 filter is required, let us. So, instead of taking whole spectrum, I am taking 80 point of the spectrum. So, I am taking 80 point instead of whole spectrum, I am taking 80 point of the spectrum and find out the Cepstral coefficient. I can treat that as a signal, pass through the inverse DFT and Cepstral coefficient will be generated. Okay. Okay. Cepstral coefficient can be generated. So, information is reduced. Now, the problem is that if it is a linear filter, this does not match with human perception, human frequency perception. If you remember in during my lecture on human perception of frequency and amplitude or speech perception, we said the signal, the frequency perceived by the human being is not in linear scale, this is in male scale. So, instead of taking the linear filter, now I convert the filter bandwidth as per the male scale. What is the male scale? You know this using this equation, we have already derived the male scale. So, the bandwidth of the filter is depends on the male scale. So, instead of uniform bandwidth filter, I take male scale filter. So, what is human perception in frequency? Lower frequency, our resolution is very high. That means, lower frequency we can perceive linearly along the physical frequency, but at the higher frequency we have some low resolution. That means, the band of frequency, the frequency band we perceive as the same frequency is larger. So, I can say at the high frequency region, the bandwidth of the filter will be large. So, that means, we do not require that much of coarse resolution. So, rough estimation is sufficient for high frequency. Okay. So, that is why we take the bandwidth of the filter will be larger. So, bandwidth defined by the male scale. So, if I take the male scale filter, then let us I take the male scale filter. If you find out that if it is 4 kilohertz, I think 20 filter will be sufficient to cover the 4 kilohertz frequency or entire frequency range. And so, I can get M1, M2 up to M20, because every filter give me a single point bandwidth, single bandwidth. So, every filter has a single bandwidth which is M1, M2, M3, M4. I can find out 20 male point. So, since filters are male scale, filters are designed in male scale, then we can say we have worked the LP or the frequency spectra in male scale. Instead of hertz, I work this spectra in male scale. So, what I get instead of hertz, I get male scale in here, and here is let x cap k. Instead of x k, I take x cap k. I take the average energy. So, instead of spectrum, I get male scale spectrum. Once I get the male scale spectrum, if I analyze Cepstral coefficient, then this is called male scale Cepstral coefficient. So, since my spectrum is frequency warped in male scale, that is why it is called male frequency Cepstral coefficient. So, what I am actually doing in mathematics, I am designing the filters. I will explain in the next class. First, I describe the equation. So, I calculating x cap L, L is the number of filter, x cap L using male filter bank. Over the male filter, I am calculating male spectrum, and once Cepstral coefficient is analyzed based on the male spectrum, then is called male frequency Cepstral coefficient, MFCC. Okay? Have you understand? MFCC. That is why it is called MFCC, male frequency Cepstral coefficient. Now, how do you design those things? So, what should be the block diagram? So, I am describing the complete block diagram of male frequency. So, if you see the basic signal processing block is remain same, pre-emphasis, windowing, DFT. After I get DFT, what I can do after, so if it is SN is my signal, I pre-emphasized it, and after DFT, I am not writing the pre-emphasis and windowing part. So, after DFT, I get SK. So, SK is the normal frequency spectrum. So, then from SK, if I calculate mod of SK and plot with frequency, so mod of SK is nothing but a frequency versus power plot, which is the spectrum in normal frequency scale. Now, I work the frequency scale in male scale, male frequency, or you can say the male filter bank. I pass that with the male filter bank. When I pass with the male filter bank, what I will get? I get same spectrum, but in male scale. Instead of frequency, I get S cap k, which is in male scale, or instead of k, I can here write L. L is the number of analysis filter. So, if it is a 40 filter or it is a 20 filter, so L varies from 0 to 19. Okay. So, I can get number of filters. So, once I pass through the male filter, I get male spectrum. Once I get the male spectrum, I can pass through at IDFT to get the male spectrum. OMF, I can write MFCC. So, those delta, double delta will come later on. So, I get MFCC, male frequency Cepstral coefficient. So, the mathematics is, this is the mathematics, and instead of DFT, what I will do, I will pass, instead of DFT, this IDFT can be replaced by a DCT, discrete cosine transform. IDFT can be replaced by a DCT. So, this DCT equation is this. So, S cap m or L whatever will cos pi by L m minus 0.5 I equal to 0 to C minus 1. Okay. Number of Cepstral coefficient is okay or not? Okay. So, next class I will discuss how we implement it, or I can say that let more details discuss on implementation issue on MFCC, then we discuss about the delta, double delta, then PLP and then Rasta, then the features extraction will be completed, we will go for the F0 extraction. Okay? Thank you.